Okay, so it's now 11:30. So let us start. Uh, welcome back to everyone. This is the last or fourth lecture of this topic, quantum clocks for fundamental science and metrology. So in last three lectures, I covered about the basics of atomic clocks, microwave clocks, optical clocks, some of the technological needs for atomic clocks and etc. And today I am going to talk about these atomic clocks can be used as very accurate sensors to sense some of the quantities. Those are very important to explore fundamental science. So let's begin. So as I said, so basically it's a quantum sensing and using quantum clocks, and it's basically measuring very tiny bits of perturbations. It's extremely tiny. It's like uh, basically you can say it's negligible, but if we want to study the fundamental aspects of science, it's not negligible anymore. We need to understand and we need to really measure it, whether these perturbations are actually coming from those fundamental science aspects or not. And there are many ways to measure it, and atomic clock is actually one of the most accurate tool that can measure it very accurately. It's a very promising tool to for this purpose. And the kind of science that the kind of things that one can measure, I have taken here few examples like for constancy of the fundamental constants, particularly the dimensionless fundamental constants. So the constants we have in our standard model physics, there are many like let's say human made constants we have in our known standard model to explain the basic physics, but these constants may not be constants. Nature doesn't define any constants. It's defined by human beings. So we have to really measure whether these human-made constants are really constants for a very long period of time or not. Similarly, violation of the fundamental symmetries, let's say Lorentz invariance violations and these kind of things. Also, the atomic clocks can actually detect gravitational waves in the future. It's not yet sensitive enough to measure that, but in principle, it can do it. The LIGO, or basically there are several other gravitational wave detectors which can measure it, but it doesn't measure in over the entire band. At very low frequencies, particularly, it cannot measure it very accurately. But atomic clocks probably are the way to measure them. So there are also proposals to measure gravitational waves using atomic clocks. Then geodetic measurements that I already explained in my last talk. So let's not go into detail of that. Also, atomic clocks basically can measure dark matters indirectly. Indirectly, what do I mean? Like if there are, well, we know there are dark matters and etc., but there is no direct measurement yet. But this dark matter actually influences several other changes which can be measured directly by atomic clocks, and that can explain that whether the dark matter is actually there or not, or basically indirect measurement of the dark matter. And optical clocks are very useful tool for next generation communications, or let's say basically quantum information processing. So each of these topics are actually quite vast. So it's not possible to cover all of them in one single lecture. So I have picked up actually only two of them, actually three of them. One I already explained you yesterday, that is geodetic measurement, like mapping geopotential of entire Earth's surface with 1 millimeter or sub 1 millimeter accuracy, that I explained in my last lecture already. So today I will cover that how atomic clocks are used to measure constancy of the fundamental constants, particularly the fine structure constant. I will take an example of the fine structure constant, and also violation of the Lorentz invariance. So these are the last these last two things that I will cover in today's lecture. So let's begin. So what do we understand? What do we understand by constants? Well, constants. What I mean by physical constants in our science, what we study. So there are different type of constants that we consider in our models to explain physical nature of particles and etc. Some of them are universal constants, like let's say this capital G or Planck's constant or velocity of light and etc. Then there are some constants which comes from the electromagnetic interactions, like let's say charge of electrons, Bohr magnetron, nuclear magnetron, and then eclipsing constants, and so on, so on. Similarly, many from the atomic and nuclear physics, like Bohr radius, then these Landesi factors, then proton mass, neutron mass, and so on. There are fundamental particles, and there are several physico-mechanical constants, like let's say the this R is gas constant basically, and then uh, uh, mole and etc. Boltzmann constants and so on. But all these constants, what you see here so far, these all have dimensions. So now, if we want to measure uh, these constants, then it will always depend on accuracy of the scale. Let me just take a simple example. Let's say I want to measure temperature of a surface. Then I have to use some thermometer to measure the temperature. But how accurately I can measure the temperature depends on least count of the thermometer. So I cannot do any measurement better than that because it has some dimensions. So I am measuring directly the temperature, which has some dimensions. Instead, if we have some constants which are dimensionless, basically which are independent of the scale that you are using, then that is not basically depends on how accurate or inaccurate is your scale is. So those constants, measuring constancy of such constants which are dimensionless would be much more efficient for fundamental science aspects, from fundamental science aspects. And there are several dimensionless fundamental constants. For example, coupling constants for electromagnetic force, that is like fine structure constants, alpha, and it's typically 1 over 137, we know, but this has a much precise value than just like 1 over 137. And similarly, coupling constants for weak force, coupling constants for gravitational force, basically coupling constants for all four fundamental force, then proton to electron mass ratio, then there are also cosmological dimension constants like density parameters and so on, so on. So these are few examples. So as I said, so if we have to really measure whether these constants are fundamentally constants or these we just consider to explain our models, then we have to measure these values very, very accurately over a long period of time and basically try to find out whether this has changed over time or not. So for that, dimensionless constants are much better quantity to measure than any other constants which have dimensions like this upper row and etc. So today I will take the example of fine structure constants, and it has been explored quite a bit so far to measure whether that fine structure constant is really a constant or it has changed over time or not. So this question was first asked or raised by Buckle in 1967. And this is the paper what you see on this screen. This is just in one page physical review letter paper. So you can understand that uh, importance of that paper, that he found something and then he published it very quickly. And he basically analyzed the data that was available at that time from some fine structure splitting of some quasar spectra and etc. And he gave an upper bound for variation of the fine structure constant is something like on the order of 10 to the power minus 12 per year. And then the actual investigation started in 1999. That was in University of New South Wales. So they have a theoretical group who was working on astronomy, analyzing the astronomical data, basically quasar spectrum. And by looking at this quasar spectrum very in detail, they gave some value, and they also have some theoretical group in the same department, and they analyzed it further and basically predicted what could be that value. So if I start from 1999, like when, let's say, more accurate data were available at that time from quasar absorption spectra. So since 1999 until, let's say, today, the experiment have evolved in such a way that we are able to measure like 2 orders of magnitude more accurate for the alpha violations than 23 years back, let's say. Uh, but still, these are all upper bounds. There is no exact measurement of alpha violations until today. So all the experiments, there are several other experiments. I'll speak about all those different experiments in a minute or so. But there are different ways to look into possible alpha violations, but none of them actually could measure any actual value of the alpha violations, but they gave an upper bound. So that means if there is any alpha variations that is below than those values. So there are two, well, practically speaking, it can be divided into two different, like let's say, categories to look for alpha violations. One is observing something which has happened very, very long time ago, like in a cosmological time scale, like billions or millions of years ago. So that is one way to, and then you observe it today. Since it has happened billions or millions of years ago, then if there was any violations, if any variations on alpha, then you would be able to measure it today by accurate measurement technique. And there are two ways this kind of this kind of phenomena can be observed or experimented. One is looking into electromagnetic spectrum emitted by quasars. Quasars, this is like highly active, like uh, part, like what do I say? Some objects at a very, very far distance from Earth, like 600 million light years to some tens of billions of light years away from the Earth, and that emits electromagnetic spectrum. And these electromagnetic spectrums are basically coming from fluorescencing from some atomic transitions and etc. And this atomic energy levels depends on fine structure constant, value of the fine structure constant. So basically the idea is, if the fine structure constant have violated over this long period of time, then by comparing a spectrum that was emitted some hundreds of billions of years ago and comparing that with something today, then there will be a discrepancy. So from there, with proper theoretical models and etc., one can find out whether if there is any variations of the fine structure constants or not. And that's the spectra, sort of an one example spectra I am showing here. So what this like let's say the astronomy or astrophysics people do, they measure different spectra from different atomic or ionic species. Here you see that ionized iron, ionized magnesium, and ionized silicon spectrum. So the spectra are actually expected at some particular position by proper calibration, but they appear at a slightly different position in wavelength or frequency than what is actually expected. For example, here you see for iron 2, actually expected is this dotted line, but it has shifted to somewhere else here. This is just an example to explain this thing. And this shift is corresponding to the possible alpha variations. But this is not that easy. So you have to really calibrate everything. You have to correct for the red shifts and etc. etc. So it's a very complex example, but in an easier way, that's the whole idea. So you measure the spectra in your lab frame, which has happened billions of years ago, and then compare it with a reference in your lab frame, and then see whether there is any discrepancy or not. The other thing is looking into natural reactions, natural nuclear reactions. Natural nuclear reactions, because natural nuclear reactions happens over very, very long period of time, not the man-made nuclear reactions which are very controlled and you can do it, you can stop it, but natural nuclear reactions cannot be stopped. And one such phenomena does exist on our Earth, that is called Oklo uranium mine in Gabon. This is in West Africa. So this is actually a uranium mine where the nuclear fission reactions are happening over last 1.8 billion years. Yeah, so just after beginning of Earth and etc., something on that order time scale. So, and this the people found there is a discrepancy of what do I say, natural abundance of uranium 234 isotopes. So naturally, uranium 234 isotopes are 0.72% abundant. But in Gabon, what they found, this is 0.6%. So this is different than what we expect naturally. And this discrepancy, this anomaly is possibly because the alpha, value of alpha, fine structure constant has changed. So there is a proper nuclear model where this alpha comes, and then they explain that possibly this discrepancy is due to the violations, the variations of fine structure constant. So these are the two different ways where one can basically measure fine variation of fine structure constant, which are occurring for last billions of years. One was quasar absorption spectra, which was emitted 100 billion years ago or something like that, and one was looking into the nuclear fissions, which actually have started, let's say, 2 billion years ago, and so on. Okay, so there is another way to look into it. Rather than looking something at very which has happened at very past, one can also look into something which is happening right now. Like I am talking and these things is happening, and I can measure and intercompare such events and can also detect whether alpha is varying or not. So basically present event rather than very, very past events, present events. And there are also several experimental ways to do that. One is optical clock comparison. So I have an optical clock here. There is probably another optical clock, let's say somewhere else in the world. And then very accurate measurement of this clock transitions. I will actually explain it in more detail later on. And then comparing that over some small period of time, that can also give whether alpha is varying or not. The other possible thing is the concept is basically same as optical atomic clock comparison, but instead of an atom or an ionized ion, basically instead of looking into electrons, one can look into the nuclear transitions. And nucleus is actually extremely least perturbed, like nearly negligible perturbation compared to the electrons. They are not easily perturbed by electric, magnetic, or any other stray fields and etc. The problem with nuclear transitions are they are in gamma rays, and the transition frequencies are not easily detectable very accurately. When I mean easily not detectable, means very accurately. But in thorium 229 nucleus, there is one transition which is in the optical domain. It's in a very deep UV domain at 150 nanometer. This is something, let's say, like an let's say it's not usual thing. It's only so far found in thorium 229 nucleus, and this transition is just observed few years ago. It was predicted quite few years ago, but it is observed with some level of accuracy just 1 or 2 years ago. The point is these thorium nuclear states have very high sensitivity on fine structure constant, and the sensitivities are 3 to 5 orders of magnitude that one can expect for electrons in general. So since it's highly sensitive to the alpha, that means if there is any tiny bit of variations of alpha, that can be easily predicted by looking into the thorium nuclear transitions. Okay, and people are actually working for that, but it's in very early stage. People are trying to find out this transition more accurately at this moment. The another candidate is actually dysprosium. Dysprosium has few isotopes. The uniqueness of dysprosium is it has, you see here this marked this rounded marked things, and it has actually two energy states which are opposite in parity. But these two energy states are nearly degenerate. That means these two energy states are almost at the same energy level. The discrepancy is only about 200 megahertz or so. It's very unique thing, unique feature. And one of these states is highly sensitive to fine structure constant, whereas the other state is not that much sensitive. So as a result, what will happen if you can measure the energy difference between these two states very accurately, then over time you will see that difference of energy between these two states will change. And how much is it? Just a quantitative analysis. Let's say the alpha variation rate is 10 to the power minus 15 per year. If you use this value just as an example, then you expect that this energy level difference between these two opposite parity states of dysprosium will be 2 hertz per year, and that is measurable. But of course, the rate is actually much lower. The rate of alpha variations is much lower because people have already reached to this level of sensitivity, and people could not make any distinction between whether there is a change between these two energy levels and etc. etc. So far, there are also other possible ways to measure alpha variations which have been proposed, like in looking into the ultra cold molecules or highly charged ions, but people are investigating at this moment. Whereas the this atomic clock, optical clock comparison has actually reached to a very sensitive level. This is already happening over last 1 decade and so on. And every year, basically, people are making more and more sensitive clocks, so they are reaching to a different level of sensitivity or upper bounds every year. So, in a nutshell, basically, there are two type of experiment. One is looking into past events, and one is looking into present events. And if I compare like quasar absorption spectra and optical clock comparison, then practically speaking, optical clock comparisons are much more accurate and sensitive compared to the quasar absorption. Looking into the quasar absorption spectra, and the main reason is basically in the quasar absorption spectra, you are detecting the spectrum by astronomical telescopes and etc. And resolution of astronomical telescopes are not that great. So inverse of the resolution is basically delta nu by nu, or resolution is actually lambda by delta lambda, or nu by delta nu. Then inverse of the resolution is delta nu by nu, which is for the best case scenario 10 to the power minus 5. Whereas for optical clocks, this delta nu by nu, that the sensitivity of the optical clocks at present is it's on the order of 10 to the power minus 20. So that means you can measure frequency of an optical spectra much more accurately in optical clocks than what you can do by using astronomical telescopes and etc. But that doesn't mean that one should not do the quasar absorptions studies, because see, that has a different type of physics inherited into that compared to the optical clocks, because there you are actually looking into some spectra which has seen alpha variation in its on its way. But in place of optical clock, you are comparing some present event. So actually, if at the end we have to conclude whether alpha is varying or not, we have to study in all different possible ways. And finally, all of them should give the same answer. So it's never true like one should only follow one particular path, like let's say optical clock, but one have to actually study from all these aspects, all possible experiments, and finally they should conclude the same thing, and then only we can consider in our standard model that okay, alpha is varying at that rate and so on, etc. Okay, so if let's say if we find that alpha is actually varying, it's not a constant over cosmological time scale, that will indirectly tell you the existence of dark matter and dark energy, or actually conversion of dark matter and dark energy to the real matter and real energy at some very slow rates and etc., which possibly changes the values of alpha. Okay, it can also give indirect measurement of the vacuum fluctuations. What do I mean by that? Like what we call vacuum is not real vacuum, it's actually breaking into electron positron pairs and again annihilated, and that rate is probably also changing in case alpha basically changes or not. Similarly, like it itself violates the equivalence principle also, because that means the experiment should depend on measurement, should depend on the reference frames and etc. etc. So now let's say that one at the end of the like all these experiments, we find that alpha has a small rate of variations over cosmological time scale, and that might actually lead to grand unification of the standard model. What do I mean by that? At the present, standard model doesn't include the gravitational force. Gravitational force cannot be explained by quantum mechanics so far. But all these experiments, this is only one of them, what I am telling you, like alpha variations, but there are several other experiments, and alpha variation is only one among them, which are needed for these grand unifications for the standard model. So it's basically contributes to the fundamental science. And optical clocks, and bottom line is basically optical clocks can be used as a sensor for studying this fundamental science. Okay, now let me focus on atomic clocks, how it can be used for alpha violation measurements in a more detailed way. Okay, alpha, I already told you, this is like 1 over 137 point several digits. People have measured this value of alpha very accurately through different experiments, and these values are given in the core data, international core data. This The important part is this alpha can be written into two parts. One is E square divided by 4 pi epsilon naught times 1 over Planck's constant times C. And dimension of the first part is inverse of the dimension of the second part. As I have written here, energy times distance, and the second part is inverse of the energy times distance. Now these two dimensions cancels each other, and that's why as a whole alpha is a dimensionless constant. Okay, now let me do a little bit more. This quantity h bar times c, that can be written in terms of phi 0, where phi 0 is the magnetic flux due to the spinning of the electron. It's an electromagnetic interaction, so electrons have some spins, and the spinning of the electrons are creating some magnetic flux, that is the phi 0, and that can be written in terms of phi e and phi m, basically electric flux and the magnetic flux component, in two components. If I take a partial derivative of this quantity h bar times c, that is delta h bar c divided by h bar c, then basically I get some sort of constants times delta phi e over phi e plus delta phi m over phi m. The important thing is there is a plus sign here. Okay, now let me take the other part, that is E square by 4 pi epsilon naught. And okay, sorry, not the other part, actually the entire part, alpha. So the alpha is E over 4 phi 0. Phi 0 is again magnetic flux due to spinning electrons, square root of mu 0 over epsilon naught, and that again can be written in terms of phi e and phi m. If I take the partial derivative of alpha, then I get another constant. So this constant is not same as this constant, that's just a different constant. And then I get delta phi e over phi minus delta phi m by phi m. So there is a negative sign here, and here is a positive sign. Okay, so far so good. Two are different quantities, so sign doesn't matter. But now let's say we know that total electromagnetic energy should be conserved. Now this is actually related to the vacuum fluctuations. If the vacuum fluctuations, this phenomena is constant over like let's say cosmological time, then we can consider electromagnetic energy is conserved. But if that is different, that has changed, then the total electromagnetic energy probably this also should have changed over cosmological times. So for now, let's say forget about all these vacuum fluctuations and etc. Let's say the total electromagnetic energy should be conserved for an electron. Then delta phi e by phi e is equals to negative sign of delta phi m by phi m. Okay, now on the other, if I use this into this delta alpha by alpha relation, then delta alpha by alpha is not is equals to 0. So that means there should be a violation of the variation of the alpha. So if I consider total electromagnetic energy of an electron as a constant, then alpha have to have. Okay, on the other hand, if I consider alpha is constant, there is no change of alpha over a long period of time, then there will be a violation of the energy conservation. So something else. So these two are like doesn't explain the same thing. There is something, there is an anomaly. So this is a very simple way to understand that from where, like why this is so much important, that to look whether alpha is a constant or not, or on the other hand, whether the total electromagnetic energy of an electron which is bounded on an atom is constant over a very long period of time or not. Okay. So as I already said, that there are different experiments people have tried, and among them the most accurate one is the optical clock comparison, and there are few values I have quoted, and also there are corresponding references, and the most recent one is at 0.01 times 10 to, so let's say 10 to the power minus 18 per year. So that is the most recent, not value, actually upper bound. So that is sensitivity of their experiment, and that is upper bound of the possible alpha variations. Looking into the quasar absorption spectra, so our own colleague Professor Srianand looked into spectra, optical spectra from quasars, and his predicted value was something like around 10 to the power minus 16 per year. And our neighbor from NCRA, Nisin Kanekar, he also looked into the radio frequency spectra from quasars, hyperfine lines of the spectra, and from radio frequency side, he also gave, it's actually in radio frequency, in hyperfine spectra, one cannot distinguish mu. Mu is the electron to proton mass ratio, and alpha. So it's a together conjugate quantity, and the predicted value is also on the order of, let's say, 10 to the power minus 16 per year. Well, when I say predicted value, that means upper bound. There is sensitivity of the experiment, but not actually the violations of the variations of the alpha and so on. The Oklo uranium mine gave sort of the value 10 to the power minus 17 order and so on. The dysprosium experiment, that gave a value of 10 to the power minus 16, on the order of 10 to the power minus 16. And there are also proposed other method, but as you see that okay, no, there is something else. So okay, as you see that so far the optical clock comparison can actually measured it most accurately compared to all other methods. But as I already said, that all other methods are equally important as for the optical clock comparisons, basically to get the same physics out of everything. Now, why optical clock comparison? So in the optical clocks, basically we are measuring the energy difference between two states very, very accurately. I explained the principle of the optical clock in my second lecture. So energy level of an atom, one can write like this Bohr Sommerfeld model and all these corrections and etc. And you can see basically there is a dependency on the value of alpha. This is only in first order, but if you take higher orders, this is proportional to alpha square, alpha cube, alpha to the power 4, and etc. So most of the contribution comes from non-relativistic contributions, and then there is a relativistic corrections of the energy level structure or atomic structure calculations, which depends on different exponent of alpha. It basically goes up to infinite, but their values decreases slowly, and it's nearly impossible to calculate up to all order of alpha, because it requires such an extremely high computational part. It's not possible to calculate, but one can of course measure it. Only thing is how sensitivity is your measure. Then the third part is finite size of the nucleus, because every isomer have different number of neutrons, and then size of the nucleus changes, and that also shifts the energy levels a little bit. So now the point is, basically the take home message is like any energy level has an alpha dependency. It's not only alpha, and this dependency is different for different atoms or different energy levels of an atom, and that says which atom or a particular state of an atom is how much sensitive to alpha variations or not. So there is a sensitivity factor comes from that aspect. So basically if I simply write energy level difference between two states, that is, let's say, our clock transition, then I can write it in terms of some constant in a simple word, and then function of alpha. If I take a partial derivative, So this delta E I can write as a clock frequency times Planck's constant, and if I take a partial derivative, then I get this part which is time derivative. Sorry, if I take a time derivative of the clock frequency, then I get a time derivative of alpha, or this functional form of alpha. And if you do a little bit more mathematics, which we don't need to do at this moment, then if I look into the fractional change of the clock frequency over some time period, then I get the sensitivity factor times fractional change of alpha variations. And this sensitivity is different for different atoms or ions or different species basically. As I said, that depends on uh, properties of the atoms and etc. etc. So here what I am showing sensitivity for different species. These are, for example, neutral atoms. These are singly charged ions. These are highly charged ions. This is nuclear, like thorium is most sensitive. So this is scaled down by 10 to the power 3 to put them into the same plot. Then dysprosium or other elements, which is microwave transitions and molecules. So this is sort of all the elements that have been investigated theoretically or experimentally to find out their sensitivity factors. And among them, thorium has the highest sensitivity. It's still under exploration. The like experiments are still in the very early stage. Whereas ytterbium ion is one of the very good candidate. It has also very large sensitivity for to look for the alpha variations. And if I just simplify that plot, so basically I am only considering few ions, singly charged ion, and few neutral atoms which have been used as a clock in different parts of the world. Then ytterbium ion, the clock transition of ytterbium ion has the highest sensitivity among all the other optical clocks. So ytterbium ion is a very good candidate if somebody wants to measure the alpha variations using it. That's what I wanted to basically tell you. And just to compile all the results from different experiments to look for alpha variations, and these are the different color codes like atomic fountain to atomic fountain comparison, then optical clock to atomic fountain comparison, optical clock to optical clock comparison, looking into quasar absorption spectra, looking into this OCLO data from nuclear fission, and also accurate measurement of this dysprosium energy levels difference and etc. So if I plot all of them, I have plotted all of them together, and you see that ytterbium ion clock comparison gave the best result so far. That is just in last year. The best upper bound so far is coming from ytterbium clock transition spectroscopy. Okay, so looking into the time, this I have to skip. If somebody have questions, I can come back. So basically, I skipped the part where I wanted to tell you the alpha variance, sorry, the local Lorentz invariance violation measurement using the optical clock. I don't think I would be able to cover that part in 1 hour lecture. But if somebody is interested, then I can tell you few words at the end. So now we have explained optical clocks, the principle of the optical clocks, different types of optical clocks, and how these optical clocks can be used for just for accurate time keeping, and also for exploring fundamental science. But the point is, if somebody is building an optical clock, he has to keep in mind several things. And three important things is how, why, and what. So basically, what I wanted to say that you need to know what exactly you want to plan, you want to do using the optical clocks. Do you want to use them as a frequency standard, as a just as a clock, or do you want to use them as a sensor to measure some fundamental science test and etc. So accordingly, you have to choose the species. As for example, ytterbium is a very good candidate if somebody wants to study fundamental science using optical. Yeah, so that's how one have to choose that which species you want to choose, you want to take up for building the optical clock, and from that point of view, there are few laboratories, actually not several, few laboratories in the world, they have developed optical clocks in their labs, and the pioneer is the NIST in USA, National Institute of Standard and Technology. They have all the best optical clocks in the world. It's either based on neutral atoms or based on ions. So these are like these blue ones are ions and the red one are neutral atoms. So they have different species they have tested, and they have the best optical clocks in the world. Then in Europe, in UK, Germany, then France and Italy and Netherlands, they have built several optical clocks based on neutral atoms as well as single trapped ions. Japan is another hub where they have lots of very good quality optical clocks, and actually the neutral atom optical clock, the concept comes from Japan. So they have very good quality neutral atom optical clocks, and they also have ion clock. And the Australia is actually developing. They don't have any operational optical clock at this moment. In India, particularly, there are 4 places where the optical clock activity is going on. We don't have any operational optical clock at this moment. In NPL UK, they want to build, sorry, not NPL UK, NPL Delhi, CSIR NPL, they wanted to build an optical clock where, because they are timekeeper of the nation, so they have to build more accurate clocks always. So they are interested from that point of view. At IUCAA, I am building an ytterbium ion-based optical clock, and I am interested to study fundamental science, particularly to search for alpha variations and so on. And just 3 kilometers away from IUCAA, ISSAA Pune, they are building a strontium atom-based optical clock. And the reason is the strontium and ytterbium, these two optical clocks can be compared, and these two are very good elements to do the alpha variation measurement. So this is the reason why both of us, like myself and Umakant Rapol in ISSAA Pune, we came together and we are building 2 different clocks in our locations, and these 2 clocks will be connected by highly stabilized optical fibers, and in the future that will help us to measure this kind of fundamental physics test and etc. etc. In IIT Tirupati, they are building optical clocks, but their goal is basically miniaturizing the entire clock technology. They want to produce a clock, a very compact clock, which can be taken from one place to the other place, and eventually probably in the space also. So, for example, this geodetic measurement, or if you remember, I was talking about measuring the height of Everest. There you need a compact clock. You cannot take the entire laboratory there. So that is another aspect where one has to work on, and IIT Tirupati have started working on based on calcium ion. They wanted to miniaturize the entire technology. Okay, having said all these things, in last few minutes, I want to spend that exactly what we are doing at IUCAA. So at IUCAA, we have started a new lab. It's called Precision and Quantum Measurement Lab. It's actually entirely developed in during the COVID time, and in this lab, we aim for quantum metrology measurements, precision tests, and developing quantum technologies. So this is part of the India's quantum mission. There are several labs which are working on several aspects of the quantum technologies, and IUCAA, this PQM lab, is also working for that. So practically speaking, what we have to do, we have to develop a laser, a photon which has highly stabilized in its frequency and phase. But if you take any laser, any extremely good quality laser, it's still unstable. So the instability, which is defined by Allen deviation, for a very good quality laser is on the order of 10 to the power minus 7 in 1 second. And for this fundamental science test, we have to bring it down to 10 to the power minus 17 level at least, or be better than that, to these photons. And for that, we have to do many things which is very complex, not trivial things. So just quickly speaking, so these, as I said, that lasers have this kind of instabilities typically. So for fixing that instability, we first have to develop a reference optical cavity. So this reference optical cavity itself will be very, very highly stabilized, and the stability would be on the order of 10 to the power minus 16 or 17 level in 1 second. And that's itself a very complex technology. I'm not going into detail of this technology because each of them are like individual lectures and etc. But you see here that we have already designed this Fabry-Pérot cavity, and this is under construction at this moment. And taking that as a reference, one can feed back the signal to the laser, and then this instability can be reduced to 10 to the power minus 16 level for the laser. Okay, but that's not enough because this reference cavity is made of some material. So they will slowly drift. Slowly means over years time scale or months, several months of time scale. And that drift is particularly small change of environmental parameters or aging of the materials that we use for developing this Fabry-Pérot cavity. So for that, to stop that, we need an absolute reference. Sorry, let me skip that. For that, we need an absolute reference, which is actually the atomic transition frequency. And that's where the optical clock we have to build. So optical clock gives the atomic reference point. It measures the clock transition very accurately, and that gives the absolute reference point, which doesn't change over time unless we consider alpha variations and so on. And that's exactly what we want to measure. So we have to develop a clock, and we are developing based on ytterbium ion, and there we have to stabilize this entire system with respect to ytterbium ion, and then it will be highly stabilized. It will be like let's say uh, ideally stabilized. Okay, one can ask that why do we need the ultra stable cavity? Why don't we do the entire thing with optical clock? Anyhow, we are building it. The reason is optical clock cannot be operated for 24/7, 365. You can operate it like let's say tens of days, 20 days, maybe for a month, but then it requires to fix many things like changing the intensity of the laser, stabilizing the laser, atoms and ions will be, you have to fill up, you have to work something with the vacuum system. So you always need some corrective actions to the thing. So that's why you have to have a standalone reference systems which basically an holdover, which gives an holdover. It's like a sort of a generator. Yeah, once the light is gone, then you can start the generator and it can hold over for some period of time. But that generator have to be also very stable, and that's why we have to have this ultra stable cavity as well. In simple way to understand that. Okay, so we have also developed the ion trap systems. This is the vacuum chamber. It's very we have developed it in our laboratory already, and we are putting them together at this moment. And then once you do everything correct, once you produce these highly stabilized photons, then you have to transfer these photons from one location to the other location. For example, from IUCAA to ISSAA Pune or vice versa. So that you cannot just do it by simple optical fiber communications, but the fiber length also have to be stabilized. Otherwise, you will see the photons phase will appear into a arbitrary phase into the other locations. So this is called phase stabilization of the optical fibers, and these optical fibers, as you can see, it's from kilometers to several thousands of kilometers longer. It's not necessarily have to be from ISSAA to IUCAA, but it could be to an intercontinental distance, to a different laboratory in different continent. That's actually already happening. But in India, we have to develop this technology. So that is a third technology what we also have to develop ourselves in the country, and we are working for that. So let me skip these things. So at the end, wanted to give you an impression about the lab, which is actually what you see here is the PQM lab at IUCAA. So this is the video. You see there we are like designing all these complex things. So this is the optical cavity that we have designed ourselves in the lab. And this is the inside of the clean room area where the actual experiment will be built. At this moment, some electronics experiments and testings are going on. Soon we will start putting the vacuum chambers together and actually the ion trap systems and etc. etc. Okay. So having said that, let me conclude by saying that what we are doing at the PQM lab in IUCAA. So we are building a state-of-the-art experiment of basically developing an ytterbium ion optical clock. This development requires interdisciplinary expertise. Like starting from physics knowledge to vacuum systems, optical systems, electronics, and software development. So we have to work together. We have to have physicists, we have to have engineers, and they all have to work together and bring things together so that everything can work at the same time. So it's a really, really collaboration between interdisciplinary areas. So it will actually, India have a high demand of human resource, very qualified human resource in quantum technologies. So PQM labs shall generate very high quality human resource, which will be useful for India's quantum mission and for other experiments also. It has national importance because clock itself, optical clock itself, has many strategic applications. So upon development of the optical clock in the PQM lab, it will have lots of national importance. And it also has global demand because it's part of the quantum missions. And we know that at this moment, basically the world is realizing second quantum revolution. And similarly, India, government of India is also interested, and they are also emphasizing their research into the quantum technologies and etc. So it has lots of global demand. And finally, we as a physicist, we are always interested in fundamental science. So upon development, these optical clocks will be actually used for fundamental science test. Okay, I'll stop here and then I'll take questions. So there is one question by Tanmoy Pati. For change in alpha HC product, what is HC? Okay, Planck's constant times velocity of light product will change. So does it mean all energy leaves we have measured need to be corrected, which can be considered as problem of prediction of quantum metrology? Actually, sorry to say, I do not understand your question. Is it possible you can speak? So if I understand correctly, then you are saying basically your question is, if alpha is varying, then whether what is QM, quantum mechanics or quantum metrology? So basically, if I understand correctly, you are trying to say if alpha is varying, then whether we have to have change in our knowledge, let's say standard model. That's what probably you are saying by QM, quantum mechanics. So yes, the answer is yes, and that is called uh, what is it called? Extension of the standard model. So our standard model considers alpha as a constant, and that's how the standard model is derived. But if alpha is varying, then we have to change things in our standard model. Like for example, the quantum electrodynamics, where this vacuum fluctuations is considered, but this vacuum fluctuations energy is conserved. But if alpha is varying, maybe that energy is no more conserved, but that is transferring to some other form of the energy, and that is extension of the known standard model. I hope I understand your question correctly,
Yes,
even
sir.
though I'm
Thank you,
yeah.
sir.
Okay. And then there is a question by Thomas Yakub. Yeah, your hand is up, so can you please speak?
Okay, sir. Can you hear me?
Yeah,
Sir, my question is, you mentioned something about the use of lasers in the quantum high accuracy clocks. So,
yeah,
is squeezed light, I mean, the quadrature squeezing of light or squeeze light any use in
yeah, right,
this
yeah,
accuracy?
yeah, yes, actually yes. So uh, let me go back to this slide. So the I don't think the squeeze light is useful for actually. I mean, I don't think squeeze light has any use at this moment for the lasers that we want to use for measuring clock transition. But the squeeze light will be very much useful for the photons that we want to transfer through the optical fibers. Because if they are squeezed in the phase quadrature, then at the end of the fiber, you also wanted to get the same phase quadrature, so you can enhance the accuracy of the measurement or accuracy of the transfer these things, provided you use a squeeze light. So these things are actually already in under investigations. How to use, I mean, the application of squeeze light in this entire scheme. Yes, but the answer is yes. You are correct. So they will have importance in this kind of experiments.
Okay, thank you, sir.
Yeah. Any other questions? I don't see any other hands up. Okay, Subhodip Datta, can you please say?
Hello, sir.
Yeah.
Sir, you have lots of talk about spectroscopy. So I am just wondering, just like electric and magnetic field splits into spectral lines in Stark and Zeeman effects, right? So
Yeah.
is it possible for a gravitational field that also splits into spectral lines?
Mhm. Gravitational field splits into spectral lines. See, actually, it's only energy state which shifts by electric and magnetic field. Like if you, as you were saying, Zeeman shift and Stark shift. So what happens there actually, the energy states, they shift, they will be perturbed in the presence of electric and magnetic field, and that's why as a result you see the shift into the transition. But gravitational field is something else. It's a as far as my knowledge is there, I mean, I'm not a gravitational wave physicist, but that is not perturbed by electric and magnetic field. Even though, I mean, you can probably ask this question to a gravitational wave physicist who can answer you better. But as far as my knowledge is concerned, answer is no.
Oh, okay, sir. Thank you.
Okay. So there is another question by Pratik Thakur. The fine structure constant formula is made up of constants like so and so. Then why is it varying? Does it mean the electric charge itself? Yes, exactly. So that's the point. So the fundamental constants, like let's say the electric charge or all these things, probably they are also varying, but it's not a good idea to measure their variations directly because they are not dimensionless. So your scale might be inaccurate, and that would reflect to the variation of the dimension. There's some constant which has dimensions. So that's why people look for variation of dimensionless constants. But your answer is right. If alpha is varying, that means some quantities which is made up of this alpha, they must be varying. Okay, so I do not see any other questions. So since that is the case, so thank you for listening to my lectures, and have a good time with the rest of the lectures. So, okay.